The ship that brought down the Francis Scott Key Bridge did not fail in a storm. Her engine room was staffed, her emergency generator was ready, and her switchboard had been inspected 3 days earlier. What failed was one signal wire that was assembled wrong 9 years before, and when it let go, no alarm sounded on board. How does one loose wire drop a highway bridge into a river? That is the question federal investigators spent 20 months answering. The truth leaves a paper trail. Let's follow it. Findings of fact in the early morning of March 26, 2024. The container ship Dali lost electrical power while leaving Baltimore, Maryland, and struck a pier of the Francis Scott Key Bridge. 1/3 of a mile of highway fell into the Patapsco River, and 6 road workers died. The National Transportation Safety Board's final report traces the accident from a single terminal block on the ship to a bridge that was never assessed against modern vessels. We will follow both threads, the wire and the bridge, to where they met, a routine departure. Just after midnight on March 26, 2024, the Port of Baltimore was doing what it does every night. The Dali, a 984-foot container ship flagged in Singapore, was preparing to sail for Colombo, Sri Lanka, a 27-day run with roughly 56,000 metric tons of cargo in 4,679 containers. She had been built in South Korea in 2015 by Hyundai Heavy Industries. On board were 21 crew members and 2 harbor pilots, whose job was to guide her out of the harbor and down the channel. Above them, on the Francis Scott Key Bridge, a 7-person road crew was filling potholes on the night shift, along with 1 inspector. Overnight work, chosen precisely because the bridge would be quiet. 2 tugboats eased the Dali off the berth at Seagirt Marine Terminal. By about 1:07 in the morning, she was steady in the Fort McHenry Channel, and, following local practice, the tugs were let go. The senior pilot told the pilot in training to keep the speed at 10 knots or less. The channel ahead ran straight, 700 feet wide, 50 feet deep, and passed beneath the Key Bridge between 2 supports, Pier 17 and Pier 18. In 2023 alone, ships had made that passage 3,775 times. Nothing about the departure was unusual, but the electrical system feeding the ship's lights, pumps, and steering was, at that moment, being held together by a connection investigators would later measure in fractions of a millimeter. The day before, while the ship was still at the dock, the crew had switched the vessel's power distribution onto a transformer that had not been used in at least 7 months. The circuit that controlled that transformer's breaker contained a wire that had never been fully seated in its socket, not since the ship was built. No one aboard knew. No inspection had ever been designed to find it. And as the Dali came up to speed in the channel, heading 141, the Key Bridge lay about 3 miles ahead, 4 minutes and 9 seconds. At 1:25 and 0 seconds in the morning, the Dali went dark. The ship lost what engineers call low voltage power, the 440-volt system that runs the lighting, the fuel pumps, the cooling pumps, and all 3 steering gear pumps. The rudder froze. The bow was 3,200 feet from the Key Bridge, about 3.3 ship lengths, and the vessel was making 8.9 knots. 8 seconds later, the main engine shut down, starved of its support systems. It would not turn again that night. In the engine room, the crew scrambled to restore power, and they did in 58 seconds. Investigators would later call that response timely. 2 steering pumps came back. The rudder answered again, but it barely mattered. A rudder steers by deflecting the water pushed past it by the propeller, and the propeller had stopped. The Dali was now roughly 100,000 tons of steel and cargo, coasting, and her heading was drifting to starboard toward Pier 17, which stood just 200 feet outside the channel. At 1:25:59, the senior pilot made a phone call that would save lives. He told the pilot's dispatcher to have the authorities shut down the key bridge. The call lasted about 7 seconds. 45 seconds later, the dispatcher had the Maryland Transportation Authority's duty officer on the line. On the ship, the senior pilot ordered the port anchor dropped, and then the lights went out a second time. The 2 generators carrying the ship's load were starving for fuel. A pump that should have restored their fuel pressure had not restarted, and the power management system disconnected them. Another blackout, this time taking the high voltage system too. At 1:28:21, police vehicles rolled across the lanes at both ends of the bridge and stopped traffic. The officer at the north end asked about the road crew out on the span. He said he would drive out to warn them as soon as another officer arrived to hold his post. There was no time left. At 1:28:42, the bosun finally wrestled the anchor brake open. At 1:29:09, the Dali's starboard bow struck the northwest column of Pier 17 at 6.4 knots, about 7 miles per hour, slower than a person sprints, and more than the bridge could survive. 18 seconds. The key bridge was a steel continuous through truss, opened in 1977, carrying 4 lanes across the Patapsco River, about 9,000 feet from end to end, on 37 piers. Its main spans worked as a single connected structure. That design is efficient, but it has a consequence. The report notes the bridge was built with non-redundant steel tension members. In plain terms, there were load paths with no backup. If a main pier went, the truss could not stand. Pier 17 went. Using the standard engineering method for vessel impacts, investigators calculated that the Dali's impact force was more than 4 times the pier's lateral capacity, the sideways load it could resist, which federal engineers put at 5,509 kips, or about 2,800 short tons of force. 6 seconds after impact, span 18 began to fall. 13 seconds after impact, Pier 17 itself collapsed. By 18 seconds, spans 20 and 21 had followed. Portions of the pier, the deck, and the truss came down across the ship's bow and her forward container bays. The road crew had no warning. 6 of the 7 highway workers died in the collapse. 1 worker survived with serious injuries. He was pulled from the water by a police marine unit at about 1:55 in the morning. The inspector, who was walking a span when the ship hit, reached solid ground and escaped unharmed. On the ship, one of the 23 people aboard suffered a minor injury. No one on the Dali was seriously hurt. Investigators were unambiguous about one thing: the pilot's phone call, the dispatcher's relay, and the police shutting down traffic in under 3.5 minutes prevented a greater loss of life. On an ordinary day, more than 34,000 vehicles crossed that bridge. The system for stopping cars worked. The report is equally unambiguous that no effective system existed to warn the workers already out on the span, and that this gap contributed to the loss of life. One loose wire. Why does a healthy ship go dark? Through April, investigators put the Dali's electrical plant back into its accident night configuration and ran it. For 2 days, nothing happened. Then the blackout happened again, on its own, at the dock, with instruments watching. They traced it to the control circuit of a single high-voltage breaker called HR1, the breaker feeding the transformer that powered the entire low-voltage system. Inside that circuit, engineers checked connections point by point and found one wire. Investigators called it Wire 1, sitting loose in its terminal block. A terminal block is just an organized socket. A spring clamp presses the wire's metal tip, called a ferrule, against a conductor bar. The ship had thousands of them. To assemble one, a technician opens the spring clamp, slides the ferrule fully in, and releases the clamp. Wire 1 had never made it fully in. During construction in 2015, a small plastic labeling sleeve, wire label banding, printed with a number that tells electricians which terminal the wire belongs to, had been slid down over the ferrule's collar. That made the tip fractionally fatter, and the fattened tip could not pass fully through the spring clamp gate. The clamp gripped only the very tip of the ferrule. The label, meant to make sure the wire went to the right place, kept it from ever being properly connected there. The NTSB's materials laboratory found the physical evidence: electrical arcing damage, tiny sparks across a gap on the clamp face and the ferrule's end, and scrape marks showing the ferrule had backed out over time until it rested on the face of the closed gate. It still conducted electricity most of the time. Investigators could not determine exactly when it finally slipped free. What they could show is what happened when it did. That wire held the breaker's undervoltage release energized, a device that opens the breaker when its control voltage disappears. So when wire 1 disconnected, the breaker opened exactly as if an operator had rotated its control switch to open, on purpose. And because the system saw a normal, deliberate action, investigators found no warning or alarm sounded. The engineers reconnected the wire. Everything worked. They pulled it loose. Blackout. No alarms. The accident reproduced on command. The second blackout. The loose wire explains the first blackout. It does not explain why the ship could not recover. The crew restored power in 58 seconds. Textbook. What undid them was a humbler machine, a fuel pump. That night, fuel to the 2 online generators was being supplied by a flushing pump, a pump being used as the service pump. When the blackout cut its power, it stopped, and unlike much of the equipment around it, it was not designed to restart itself when power returned. It waited, silent, for a human hand. Fuel pressure to the running generators decayed. About a minute after the lights came back, both generators began to falter, turning too slowly, an under-frequency condition. The power management system did what it was programmed to do. It started a standby generator, and it disconnected the faltering pair. But it disconnected them before the standby machine had synchronized. Blackout number 2. This time the whole plant, high voltage and low. Here is the detail that should have been a warning. The day before, at the dock, the Dali had blacked out twice during maintenance. The NTSB concluded that the second import blackout and the second underway blackout had the same cause: insufficient fuel pressure, because the flushing pump could not restart itself. The same failure mode, 24 hours before the accident, with the ship safely tied up. It was in the aftermath of those import blackouts that the crew switched on to transformer TR1, the circuit with the loose wire, a transformer that had sat unused for at least 7 months. A third engineer did restart the flushing pump about 70 seconds before impact, and power came back once more. The emergency generator, for its part, was in its required standby configuration and passed every test afterward. None of it mattered by then. The report's finding on the crew stands in quiet contrast to the machinery. The people responded in a timely manner. The systems were configured in ways that turned one loose wire into 2 blackouts, and the inspections that might have caught the wire, a 6-month switchboard check, had been completed just 3 days before the accident, contained no specific guidance for examining signal wire terminals. Checking thousands of them by hand, the report notes, would be extraordinarily labor-intensive. Infrared thermal imaging, which can see a bad connection heating up, might have found it. It was not part of the program, a bridge from another era. The key bridge did have protection. When it opened in 1977, 4 dolphins, massive 28-foot diameter concrete cylinders, stood in the water to intercept wayward ships. and crushable concrete and timber fenders wrapped Piers 17 and 18. By the standards of its era, it was defended. Those defenses were never upgraded. According to the bridge's owner, they retained their original specifications for 47 years, while the ships passing between them grew beyond anything its designers had imagined. The warning came 3 years after the bridge opened. In 1980, in Tampa Bay, a 609-foot bulk carrier called the Summit Venture struck the Sunshine Skyway Bridge. Nearly 1,300 feet of roadway fell. 35 people died. Out of that disaster, the American Association of State Highway and Transportation Officials built a tool, Guide Specifications, first in 1991, updated in 2009, recommending that bridge owners assess existing bridges against the actual vessel traffic passing beneath them and calculate the annual probability of catastrophic collapse. The Maryland Transportation Authority never performed that vulnerability assessment on the key bridge. The NTSB's finding is precise and worth hearing in full effect. Had the assessment been done using recent vessel traffic, the authority would have been aware that the bridge was above the threshold of risk for catastrophic collapse from a vessel collision, and had it used the method the guide specification provides, it would have had the information to identify countermeasures, stronger dolphins, bigger fenders, islands around the piers, before the Dali ever left the dock. That is not hindsight. It is the stated purpose of a 40-year-old document, applied to a bridge with a pier standing 200 feet from the shipping channel. The board did not stop at Maryland. Investigators asked how many other American bridges were in the same position and could not find out, because the owners themselves did not know. In March of 2025, the NTSB identified 68 bridges over navigable waterways belonging to 30 different owners, whose risk of catastrophic collapse from a vessel strike had never been calculated. What changed? The National Transportation Safety Board adopted its final report on November 18, 2025. The probable cause: a loss of electrical power, a blackout due to a loose signal wire connection to a terminal block, stemming from the improper installation of wire label banding, which cost the vessel propulsion and steering close to the bridge. Contributing to the collapse and the deaths, the lack of countermeasures to reduce the bridge's vulnerability. Countermeasures of vulnerability assessment would have identified, contributing to the deaths as well, no effective, immediate way to tell the workers on the span to run. The recommendations went everywhere the causal chain went. To the shipbuilder, Hyundai Heavy Industries, put proper label banding installation into your electrical procedures. To the component maker, Wago, warn users, in the product data sheet itself, that a misplaced label band can keep a wire from seating. To the operator, Synergy Marine and the Classification Society Class NK, give crews real guidance for inspecting terminal connections. Synergy, for its part, has instituted a policy of switching between transformers twice a year, so a dormant fault cannot hide for months. To the Federal Highway Administration, the Coast Guard, the Army Corps of Engineers, and 30 bridge owners, 4 urgent recommendations issued in March 2025 to stand up an interdisciplinary team and get those 68 bridges assessed. The board reports that every recipient has responded and is acting, and to bridge owners everywhere. Until the engineering is done, the cheapest countermeasure is the one that worked that night. A way to stop traffic and a way to warn the people already out on the bridge. The costs are still being counted. 50,000 tons of steel and concrete were lifted from the riverbed. The channel fully reopened 76 days after the collapse. Replacing the bridge is estimated at $4.3 to $5.2 billion, with traffic not expected until late 2030. One wire assembled wrong in a shipyard in 2015. One pump that waited for a human hand. One calculation recommended since 1991 that was never run. Remove any link and the chain breaks. That is what the investigation record shows, and it is why the record matters. 6 men went to work on a quiet bridge and did not come home. What the safety board owed them was the truth of how, and the truth is now written down. This has been Findings of Fact. Thanks for watching. Every source is linked in the description if you want to dig deeper. If we got anything wrong, let us know in the comments, we'll pin the correction. And subscribe so the next investigation finds you. Or keep watching, the next one's on screen now.